Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. Thanks for joining us today. We're going to be looking at some combination circuits, and one of the things that we're going to look at is a multiplexer. So today's video will be about the multiplexer. We're not going to get into the applications of the multiplexer, but we're just going to look at what it is and what it does and how we implement it with our logic gates that we already know. So let's get started. So, multiplexer. I always liked this name, just sounded cool. Multiplexer. It is oftentimes called a MUX, as like a shortened name for it, so it's a MUX. And what it is a data selector. It's a line selector. It selects one input and pushes it to the output. And so we can have multiple inputs coming in to the MUX, and then only one output will be coming out. And so let's go a couple bullet points here. So it takes 2 to the n inputs, and then it selects 1 using n selectors. And then there's only one output. Okay, and so that's the basics of it. Another bullet point here is that we use a function table here instead of a truth table. And I'll show you what that looks like. Okay, so 2-to-1 MUX takes 2 inputs and then outputs 1. So here is input 0, input 1. There are selector lines, and so here is an S selector line. There's only one for a 2-to-1 MUX. And then we have the output F. And then here's our function table. And it looks a lot like a truth table. And in this case, on a selector, we can have a 0 or 1 for the selector. If the selector is 0, then the output is input 0. And if the selector is 1, then the output is input 1. So here's where we see the difference, that we don't have 1s and 0s here. We have I0 and I1. And when we do the circuit, you'll see why that kind of makes sense. But for now, just understand that we're not passing through a 1 or a 0, we're actually passing through the input. And if that input changes, then the output changes along with it. It passes right through the MUX. We're selecting which input we're passing along to the output. And so that's the basic idea. And so just a bullet here, the output isn't simply 1 or 0, it is the value of the inputs I0 and I1 and whatever happens to them, whatever their values are. Okay. So let's look at what a schematic like this would look like. So how would I implement this? So we have AND gates. Remember, AND gates are highly selective, and so they're going to be a natural go-to for something in which we want to select. And so we're going to feed 2 AND gates into an OR gate, looking like our sum of products, if you will. And so we're going to have one of our inputs going into one of the AND gates, and the other input going into the other AND gate. Now, let's think about, what's going to happen here. So right now, this could be a 1 or a 0, and we don't know because we don't know what the other selector input is, but let's take a look at an AND truth table. and see if we can make some sense of what that selector is doing for us and what this configuration is going to do for us. So I guess maybe I should draw the selector in here. Selector is going to come in, it's going to be a 1 or a 0. So if it's a 1, I want it to activate the top AND gate. And so putting a 1 here activates that top AND gate. And if it's a 0, I want it to turn into a 1 to activate the bottom AND gate. Actually, I got that backwards. If it's a 0, I want to activate I0. And if it's a 1, I want to activate I1. So that's what we're doing here. Okay, sorry about that. And so if S comes in as a 0, then this input becomes a 1, and we activate this AND gate, and I'll show you what that means. And if S comes in as a 1, then we put a 1 to the AND gate here, and we activate the AND gate associated with I1. So on an AND gate, we activate the AND gate when our S, I'm going to call X here as our S, when our S is 1. So remember, the AND gate looks like 0, 0, 0, 1. So let's look at when S is 1 by looking at these 2 rows at the bottom here. And so when we activate, S activates an AND gate with a 1. Okay, so if that's what's happening here, then let's look at what the outputs look like. So the other thing that goes into the AND gate is the input itself. So then now the input's coming in. This is I0 coming in. We've already activated the AND gate with a 1. So what happens here? Okay, and that's what we see right here. So if the input is a 0, the output is a 0. If the input is a 1, the output is a 1. And so the output here matches the input. And that's what we want. And on the other side, if we get a 0 and we give a 0 for the S to the AND gate, then it's always 0, so nothing happens here. And so when that gets fed into the OR gate, it doesn't say anything. It's just a 0, and the 0 plus an OR gate is just the OR gate itself, right? So we look at the other side. So that's how this works. Great. So again, if you have any questions about that, please leave comments or send me an email, or whatever way it's easiest for you to contact me. I'd be happy to explain it, or if you feel like there's something else that needs to be talked about, let me know, and we can always address that in the comments or make another video. So let's go down and look at a bigger circuit here. So we're going to look at the 4-to-1 MUX. So how would we do a 4-to-1 MUX? Well, let's look at the truth table for a 4-to-1 MUX. We need 2 selectors now because we have 4 inputs, and so 2 to the n is 4, which means that n is 2. So we need an S1 and an S0. And we're going to select those 4 inputs almost like they were, min terms. So I0, I1, I2, I3 associated with row 0, row 1, row 2, and row 3. So this is our function table as we've defined it before. Okay, this is what the block diagram would look like, something like this, where we'd have our 4 inputs, I0, I1, I2, and I3. And then we have our output F, only 1 output. But now we have 2 selectors, S1 and S0. And so this would be a 4-to-1 MUX. Okay? And now the important part is the schematic. So what does this schematic look like? Well, just like we did before, we're going to have AND gates, but this time we're going to have 4 of them. Each of those will be a path for one of our inputs. So there is the 0, there's the 1, there's I3, and there is I4, or sorry, I3. I0, I1, I2, and I3. Okay, so what goes into these AND gates? Well, we have these two selectors now. And so I have S1, and I'm going to do a vertical line, sort of like we've done before for our input sections. And then I'm going to pull off a inverted vertical line as well. Ooh, okay. And then S0, same sort of deal. So we're going to do an inverted and a non-inverted line. A little squiggly. Okay, so good. And then we have our I's. So we have I0, it's going to go in right there. I1, right there. I2, there. And I3, we're going to have to like kind of bounce it around a little bit here. Okay, I should have moved that down. That's okay. I wonder if I can do that. This would be interesting. Oh, okay, not great. We'll just leave it there. Okay. So when 0, 0 comes in, we want to activate the I0 AND gate. So this is the I0 AND gate, right? So 0, 0, to activate the AND gate, we want 1s coming in. So I have to take the path here where S1 is 0 and make it a 1. And then where S0 is 0, we want to make it a 1. So we take both of the inverted paths. And then when 0, 1 comes in for S1 and S0, we want to activate I1. And so the S1 is a 0, so we have to invert it to activate it to make it a 1. And then S0 is already a 1, so we take the non-inverted line. And then for I2, we want 1, 0, so S1 comes in non-inverted, and S0 is inverted. And then for S3, so for I3, we want 1 and 1. So I can take S0 from down here, and I can take S1 as well from down here, since I drew it poorly, and then just connect it right there. So that means that when the particular input sequence comes in, we make those selectors into 1s for the gate that is associated with the input that we want. And so when 0, 0 comes in, we invert both of those zeros and feed those inverted zeros, which would be 1s, into the gate for I0, activating that gate and passing that through to the output. Okay. That is all we have for today. Thank you for watching. I hope that was understandable and that you found value from it. This is Digital Electronics Classroom. I ask you to like and subscribe and follow and all those good things. I'm Mike Stanzik, and I'm wishing you a wonderful day.